Okay, let's dive right in. I'm your host, your lead strategist for today, and we are going to unlock the examiner's playbook for one of the absolute most challenging topics in Cambridge AS and A level physics. I want you to imagine the tension right now in an exam hall. You're staring down a real Cambridge physics past paper question. Maybe it's code 0625, or perhaps you're facing 0652, 0654, 0972, 5054, or the rigorous 9702 syllabus. The clock is relentlessly ticking. Now, on one side of the room, we have a student named Alex. Alex has practically memorized the entire textbook. He overloads the page with raw physics facts, dumping every equation under the sun, but providing absolutely zero analytical structure. On the other side is Sam. Sam just rushes in, spots a number, plugs it into the very first formula he can think of, and completely misses the specific command word requirements hidden in the prompt. What's the result? Both are losing massive marks, and their papers are just bleeding red ink. Well, today we are going to navigate by the stars. And by stars, I mean your key command words. We're going to chart your course to top marks and turn all those red marks into green check marks.
Look at this quote from a senior examiner. Mastering this topic isn't just about barely passing, it is absolutely about separating yourself from the average candidate. The sheer weight placed on this specific module, turning effects of forces, which includes center of gravity, moment of a force, and the torque of a couple, makes it the ultimate watershed topic. Examiners consistently report this is the crucible. A B-grade candidate? Yeah, they can probably tell me the basic formula for a moment. But an A-star candidate? They can deploy that formula in a totally unfamiliar context involving slanted beams, off-center pivot points, and counterbalancing forces, all while systematically proving their evidence-based reasoning. They don't just calculate a number, they explain the actual physical reality of the system.
So here is our agenda for today's explainer. First, we'll cover the A-star difference. Second, defining the core concepts. Third, the procedural framework. And finally, we'll look at the top examiner warnings.
Let's move right into Section 1, the A-star difference, and how you achieve true analytical depth.
The academic benchmark demands you make a major shift. You have to move away from simply memorizing surface-level facts, that's superficial breadth, and instead demonstrate connected, conceptual understanding that transfers to totally unfamiliar contexts. That is analytical depth. Top candidates navigate by command words. Words like state, define, derive, show that, and determine are your navigational stars. If a question specifically says determine, you literally cannot just write down an answer. You must show the derivation from a fundamental principle. If you rush this, you end up like Sam, losing marks before your pen even hits the paper. Superficial breadth is Alex writing a giant paragraph about how gravity pulls things down when the question specifically asked to calculate a moment. Analytical depth, however, uses what I call the PEL framework: point, evidence, explanation, link. When an A-star candidate makes a claim about a system in equilibrium, they state the point. The system is balanced. They provide evidence. The sum of clockwise moments equals the sum of anti-clockwise moments. They explain their calculation, and they link it back to the specific physical scenario presented. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. So let's break down the assessment objectives for turning effects of forces. They target 3 distinct cognitive domains, requiring evidence-based reasoning every step of the way. I want you to do a quick interactive check with me right now. Imagine a 30-second timer ticking down. If I show you an answer that says, the beam balances because forces are equal, which domain is failing? Give it a thought. It's failing the logical structures analysis domain. Why? Because it is not the forces that must be equal for a beam to balance, it's the moments. That is the Peel framework completely breaking down at the evidence stage. Top marks demand you nail all 3 of these domains simultaneously.
Okay, moving to Section 2, defining the core concepts. This is where we learn how to avoid those nasty terminology traps. Precision here is absolutely crucial. You must strictly define center of gravity before you use it in any extended response. This avoids the terminology traps examiners are constantly flagging. Let's look at this term. Alex's original answer on a mock paper was simply the middle of an object. Bam, red X, 0 marks. The green checkmark answer, the A-star rewrite, is this: the point through which the entire weight of the object may be considered to act. Notice the exact, careful phrasing, entire weight and considered to act. If a solid beam is uniform, yes, its center of gravity is at its geometric center. But if you miss this exact definition, your entire calculation for the turning effects of a suspended sign or a balancing seesaw will be fundamentally flawed, simply because you'll place the weight force in the wrong location on your diagram.
Similarly, locking down the exact definition for the moment of a force ensures your foundational knowledge is rock solid before applying the math. Sam's rushed answer was just force times distance. And again, the examiner's red pen strikes. The precise mark-winning definition is the product of the force and the perpendicular distance from the pivot to the line of action of the force. That one word, perpendicular, is literally the difference between a passing grade and an A star. If a force is applied at an angle to a spanner, you cannot just use the length of the spanner. No way. You must resolve the force to find the perpendicular component or find the perpendicular distance to the line of action.
Finally, clearly defining torque of a couple prevents you from confusing these three interconnected yet distinct principles. A couple is a pair of forces, but not just any pair. They must be equal in magnitude, opposite in direction, and parallel but not acting along the same line. The torque of a couple is calculated by multiplying one of the forces by the perpendicular distance between the forces. Students constantly double the force or have the distance incorrectly. By memorizing this precise physics success blueprint definition, you instantly bypass a trap that catches out over 60% of candidates every single year.
Section 3. The procedural framework. The method mark strategy. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's step into our interactive workshop. This is the absolute secret to the method mark strategy. Showing your work with clear annotation is exactly how you secure those crucial process points. Let's do challenge 1, the data scan. Imagine a complex physics chart right in front of you, a non-uniform beam supported by 2 strings with varying tensions. You have 60 seconds on the clock. The average candidate tries to calculate the final answer immediately in their head. The A-star candidate uses the method mark strategy. They know that even if their final calculator punch is totally wrong, they can score 4 out of 5 marks purely by showing the correct process. They write out the principle of moments. They set up the algebraic equation clearly. It's process over outcome every time.
This 5-step standardized sequence is the exact technical methodology you should use when tackling any complex examination question on turning forces. Let's move to challenge 2, find the flaw. I'll read a sample flawed paragraph from a student. I extracted the mass as 5 kilograms, applied the moment principle, multiplied 5 by the distance, and the answer is 15. Did you catch the flaw? Take a second to find it. The flaw is in steps 3 and 5. They used mass, which was 5 kilograms, instead of force. That means they completely forgot to multiply by 9.81 to get the weight in newtons. And worse, they left off the units in the final presentation. Proper headings, correct terminology, and appropriate formats like Newton meters are completely non-negotiable.
Alternatively, you can think of it as the deconstruct, solve, and evaluate cycle. This forces you to check the validity of your answer before you move on. Welcome to Challenge 3, speed writing. You have 30 seconds to write a peel paragraph for why a crane doesn't tip over. Go. First, deconstruct the given info. You're identifying the counterweight and the load. Second, solve systematically. Take moments about the base of the crane. Third, evaluate for reasonableness. Look, if your calculated counterweight mass needs to be the size of the moon just to balance a standard steel girder, you've definitely made a decimal error. This cycle ensures that your logical steps actually hold up against the harsh light of exam conditions.
When you are tasked with interpreting complex texts and data tables, you have to extract relationships and evaluate the evidence using these exact criteria. For example, when answering a practical paper question about an experiment verifying the principle of moments, you need to state the assumptions made. Are you assuming the ruler is perfectly uniform? Are you completely ignoring the friction at the pivot point? Stating these limitations isn't a sign of weakness in your answer. Actually, it's a massive demonstration of analytical depth. It shows the examiner you understand the physical constraints of the messy real world versus a perfect theoretical model.
Section 4, top examiner warnings. Let's look at the common student traps. Principal examiners write reports every single year, practically begging students to avoid these pitfalls. Let's look at the data. This breaks down the top 3 mistakes reported by examiners, showing you exactly what to avoid. This brings us to the 3 rules that guarantee top marks. Rule 1, command word decoding. Don't use a generic approach. Match the specific context of the prompt. Rule 2, peel framework application. Don't be vague, tailor all conclusions with specific point, evidence, explanation, and link. Rule 3, the time management matrix. Don't rush like Sam and forget formats. Spend the first 20% of your time deconstructing the question, 60% solving it with clear annotations, and the final 20% evaluating your answer. I absolutely cannot emphasize this enough. Define your terms immediately. Comparative analysis requires clear similarities and differences supported by evidence. If an extended response asks you to compare the turning effect of a single force with the torque of a couple, you must establish the baseline. State that a single force produces both translation and rotation, whereas a couple produces pure rotation with zero resultant linear force. Use comparative connectives like whereas or conversely, and support each statement with the definitions we locked down earlier. This right here is how you completely dominate the knowledge and understanding cognitive domain.
To keep these rigid definitions straight, try applying a visual story method to encode these concepts into your long-term memory. Picture a perfectly balanced tightrope walker holding a massive clock. Got it? Okay, the tightrope walker's core is the center of gravity, the singular point where all weight acts. The ticking hands of the clock swinging downwards represent the moment of a force, a single force times a perpendicular distance trying to spin the walker. Suddenly, two identical birds land on opposite ends of the walker's pole, pushing in opposite parallel directions. That's the torque of a couple, causing pure rotation without knocking the walker off the wire. Visualizing this interconnected story solidifies the three concepts so you never ever confuse them under exam pressure.
Take this standardized sequence, practice it on past paper questions, and step into your next exam with the analytical depth of a true A-star candidate. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but that is only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this explainer with a study partner. Ace the Exams, your Cambridge success starts here.